computer. And we're starting today's third session where we go through some code examples for coding interview. So just to remind you, we had several sessions. So this is the coding interview. This is a local copy of my GitHub, right? So we made an overview of algorithms and the data structures. And then now we go through code examples. 1, 2, 2, and today's 3. Okay. So this is table of contents, and let's start. So the first is connected cells. So this is from HackerRank's cracking the coding interview. So this is famous Gail Lockman McDowell. She wrote a book. She has lots of tutorials on YouTube, and she's absolutely amazing. And last time I checked, she was at Facebook, working at Facebook. I highly recommend to watch her videos, tutorials, and get her book. I bought it and downloaded it several times, so highly recommend. But here is the problem. We have a matrix M by M of zeros and ones. So you see example of this matrix here. And we want to find the largest group of connected ones. So they may be connected horizontally or vertically or diagonally. So here in red, we have such a group, right? So the question is how to go through all this matrix and find different groups and find the largest one. So here, well, we have 4 groups, and the largest one is the top right, and it has 1, 2, 3, 4, 5, 6, 7 elements, right? And the approach is to use breadth first search or depth first search. Here we'll be using depth first search because it is a little easier to implement. Just a reminder, when we're doing breadth first search, that means that we create a queue. So we take something where we are, and then we start moving. It's like a wave which goes from us, and we go in layers, kind of, in as we do that. So we form a queue for the first layer, we go through the queue, and as we do that, we start populating the second layer, the third layer, and so on. This is breadth first search. And depth first search, it's usually recursive. Like you have directory structure, you go into directory, and then inside you get a list of directories and files. Now you go into subdirectory, and then you go into subdirectory. So you go in depth first, so the depth first search. So here we're using depth first search. We do dual for loop, right? So we have for loop for rows and then for loop for columns, right? And for each cell, we do the depth first search and save its size. Once we started processing cell with a 1, we set it to 0 to avoid duplicate efforts. So we destroy matrix as we go. So it's an interesting approach, right? So here we have the matrix, right? So here we get region size. So we start at some position, row and column, and in the matrix, right? And then, well, we check if we're not going outside, and then we check, and if we find one, what's happening? Okay, so we take the matrix element and we start with size 1. Okay, and then we go minus and plus. So we go row minus means we go 1 up, and this we go 1 down. And here we go left, and here we go right. And we check. What do we check? If not, row equal row and column equal column. Okay, so if if we shift, right, then we calculate region size again. So we go recursively because this is depth first search, and we edit to the size as we go. So okay, so this is a classical depth first search. So again, so we go here, we go through the for loop, we find element which is 1, right? And then starting from this element, we recursively call this function. So we already know that it is 1, and somewhere we have to, okay, here we set it to 0, right? So we change to avoid duplicates, and then we go up and down, left and right, and we continue the get region size. Okay, so this is how it is done. Next is simple breadth first search. It's a little bit different, and here we will create a queue. So find path between 2 points, beginning and end, on end by end board. Allowed steps, vertical or horizontal. Avoid cells marked T. T is a tree, so we avoid trees. So here is the code. So first we initialize the map. So here's the example of the map. We simply create a two-dimensional array and populate the grid, right? Okay, so okay, it's not interesting. Let's go through because we have a lot of material. Then init visited. So we create another two-dimensional array, which we populate as false. So it has 2 dimensions, number of columns and number of rows. And for all of them, we set value in this 2-dimensional equal to false. Okay, so we have the actual grid, which is this thing, but here it is a string. And what this code does, it makes a 2-dimensional array out of this. And here we also have 2-dimensional array of false, right? Now, endpoints have to do with limiting, okay, of the grid n by n, and we have 2 points, which is start and end, right? Okay, return row column for begin and end points, right? So we have begin points. It's better say that this is, let's here call it S, which like start and end, but whatever. So here, this procedure checks if node is on the map. Here, mark visited, we take the node and set its value to true. So these are all just small procedures to help us actually do the work. Here we check if particular node is visited or not. And here we get neighbors of the node, return a list of next possible cells, which are not tree and not start, right? And this is find path BFS. So this is actually where we do a breadth first search. And you see we're using the queue. And the queue in this case is simply a list. And we start with a starting point and then nothing else. And we'll be adding stuff to the queue as we go. So given nodes start and end, and 2 maps, grid and visited, populates the path between start and end using the breadth first search algorithm. So you can think about a wave which starts at the starting point and goes in all directions. And okay, while we have something in the queue, we take the the next element in the queue, right? And we do path dot append. Okay, what is path? Path is not here, so I don't know. No path found. We append the node. Oh, okay. Sorry. Path is here. So we take path is pop. Okay, so we're getting this tuple from the queue. We append the node, we mark it as visited, and then if it is already at the end, we return the path. We already found the path. If not, we get the neighbors, and then for all adjacent, we check if they already visited, then we are not interested. If they're not visited, then we add them to the queue. And we continue this process until we like find the end, and that will be the path which we can return. So this is the whole algorithm, and you see it is well, a lot of code. Imagine getting this problem on an interview, even if you understand how to write it. But if you're given like 15 minutes, you probably will not write it. And this is already optimized and made elegant, and still it's a lot of code. Okay, and this is actually a problem I got in one of the interview at Facebook. I mean, really, that's the exact problem I got. And I will not provide here the solution because the solution is quite lengthy. I mean, if you think about this long, like this is longer. So you've been tasked to help a village find the best place to install a new well, like water well. You're given a 2D grid. You see, this is a two-dimensional grid, and you have houses, H, and you have trees, T, and you need to put a well somewhere where the minuses is, right? So where cells can be empty, house or a tree. People can walk up, down, left and right, but they cannot walk through trees, of course. And I think they also cannot walk through houses. Find a place for the well that minimizes the total sum distance from all the houses, right? So the problem is similar to this LeetCode problem, shortest distance from all houses. And you can go on LeetCode and review it and review multiple solutions which people provide. So here is the idea of the solution. You run breadth first search wave from each house over the whole length. And in each empty cell, you accumulate two numbers. One, sum of connections to houses, right? So you want to see if this wave from particular house can reach this cell, right? And at the end, you only consider cells which are accessible for all the houses. And next, you calculate sum of distances from all houses. And then you want to minimize this number, like select the one which has minimum. So then from all empty cells, select those which have exactly n houses. So that means it's visible from all houses. And from these, select the ones with the minimum value of distance, of sum of all the distances. For each nth houses, we go over the whole area is number of rows, number of columns, which makes complexity number of houses times number of rows times number of columns. This is complexity, time complexity of the solution. Then we go over the area one last time to select the minimum, right? And so overall time complexity is this. Space complexity, we use 3 two-dimensional arrays, so space complexity is about this. If we find unreachable house, we return -1 immediately, which greatly improves overall speed of tests. Okay, so this is the problem. I have it on my GitHub. I have a solution in the repository for interview prep, so you can go there and review it, and you can also go on LeetCode and look at different solutions there. Yeah, but it's fun to receive a problem like that. So when you need to find a place on a map or like a trajectory on a map, the usual approach is breadth first search, because you can think like a wave goes and it goes around like trees and whatever, and eventually it reaches something. So breadth first search is a thing to do. Okay, topological sort, Kahn's algorithm. I tried to find the picture of Arthur Kahn, and I couldn't. So I found the original article of 1962 where he proposed this algorithm. So given a list of jobs, like you're running some jobs at night, or running some scripts or whatever, so the jobs are represented by their numeric IDs. So let's say it's 1, 2, 3, 4, 5, 6. And list of their dependencies, for example, 1, 3, 3, 2, and so on, where mn means that we need to run n before m. So this means, for example, 1, 3, that before running 1, we need to first run 3. So this is dependence. So 1 depends on 3, 3 depends on 2, and so on. So we have these dependencies, and we need to run all our jobs. So we will start with jobs which don't depend on anything, because then we can run them right away, right? And then once we complete them, we review our list of dependencies, and the jobs, for example, 1 depends on 3, but if we already finished the 3, then we can run 1. So we add them to the queue. So we first fill the queue with jobs which don't have dependencies, and then, so in this case, for example, 2 doesn't have any dependencies, so we can put it here. 4 doesn't have any dependencies, so we can put it here, and so on. 6 doesn't have dependencies. Then once we calculated this, we can calculate 3 because it depended on 2, but we already calculated 2, so we can run 3 now, and so on. So as we go, we'll populate the queue, and we run the jobs. So this is one of the algorithms. This is very common algorithm. This is very easy to understand and to implement algorithm. And so it's called Kahn algorithm. Another solution, you can use depth first search. Both have the same time complexity. And I really like the Kahn algorithm because it's elegant. So this is implementation of this algorithm. So we create the queue, and as we go through the projects, we do what I described here. And we append to the queue. Okay, I will not go through this. You can do it by yourself. Next one, binary search in sorted array. So all we need to do is implement binary search in a sorted array. So that means we divide it by half, and then we decide where we go, left or right. And then we, let's say, go left, we divide it again, and we do it to find a number which where the number is, or maybe it's not there, then we tell it's not there, right? And so that's what it does. It goes left, right, left, right, left, right. Again, it's not interesting, but many problems require you to create some sort of binary search in sorted something. And so I just wanted to show you that it's not difficult to do. It's pretty common task, or rather it is a subtask. So here we use integer division. You see, / in Python means divide, and then only take the integer part of the result. Okay, find kth largest number in the array. Okay, so this is interesting. So you can review this problem. So it was reviewed by tech lead, and solution, go through array k times, build a heap, and do k pop operations on it, and use partitioning method, see below. Okay, last time we spoke about heap structure. Remember, heap structure looks like a pyramid, and it may be maximum heap, where on the top is the maximum, and then or minimum heap. And here we go for the largest, so we'll be using max heap. And the rule of the heap is very simple. Parent is always bigger than children, and each parent has 2 children. Well, unless you're on the very bottom where the last layer may not be complete. But parent has no more than 2 children. Okay, and so here are the procedures. And again, I probably will not go through the code, but just the main idea that you use the heap and do k pop operations. So okay, this is okay. These are actually 3 solutions, right? Go through array k times. Like this is like, well, every time you do it, it's complexity is n, and you repeat it 3 times, so it's like 3n. Build a heap. I don't remember what complexity of heap is, but it's probably similar. And partitioning method described here. So this is just one of the solutions. Okay, I will not go through this because I'm looking at the time, and time flies. So let's go next one. We are given an unsorted array containing n numbers taken from range 1 to n. Okay, so we have numbers 1, 2, 3, blah, 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 n. But some of these numbers can be repeated and some may be missing. The array originally contained all the numbers, but due to data error, one of the numbers got duplicated, which also resulted in one number going missing. Okay, find both of these numbers. Okay, and this is the solution. And the solution is quite interesting because what we do, we start from beginning of the array, and then while we're going through all the numbers, here is what we do. We take the number which is at this position where we started, right? But we started at 0th position, but the number there may be some other number. It may be from 1 to n. So we take this number -1, and this will be the new index where we want to jump. And then what we're basically doing, we're jumping from place to place, trying to find a duplicate, right? Oh, okay, maybe let's go slowly to see what's going on. So we identify, so this should be the correct place for this number, right? And if the number here not equal the number at the correct place, then we swap them. Okay, or if they're the same, that means okay, it's correct place, so we just go to the next one. We don't have to do anything. Okay, and then so after we did this swapping, we then go again through all the numbers, and if number of some I is not equal to the next number, that means that this is the duplicate, and we return it. Otherwise, return -1, -1. Okay, so the idea is we go through the numbers, we do the swapping, and then we go again and we find the place where the duplicate happens. Okay, next task, jump game. Okay, you start at first index of an array of integers. In one step, you can jump ahead, or you go back, or you jump to position j so that it has the same value. So array of I equals array of j. Okay, so we need to return the minimum number of steps to reach the last index of the array. I should have provided some examples how it works. The idea of the solution is using breadth first search, starting from 0 until the last position is found. And you track all the values and positions we have explored. Again, when you're thinking about breadth first search, think about the wave, which goes in all directions. You explore all possibilities at the same time. Like wave goes in all directions, so does breadth first search. And then the complexity is O of n for time and space. So this is actually the solution from LeetCode. And okay, I'll just go to the next problem. Design around buffer to keep IP addresses. I actually got this problem on one of the interviews, and this is interesting problem because usually when people try to solve the problem, they try to think of one data structure. Maybe it's a hash, like dictionary set, or maybe a list, or maybe something else. But here you need combination of two different structures to make it work. So let's review it. So we need to design a round buffer to keep IP addresses with three methods: next IP, add IP, or delete IP. Why you need a round buffer? So suppose you have a load balancing solution, and for each next request, you need to give a different IP address. So that it goes through the buffer like round, each time giving different IP address. So you need to store current position so you can go somehow get next IP. But then you also need to maintain, for example, you decided let's increase number of servers in this round buffer, and we want to add another IP, or we want to delete IP, maybe because this server went bad and we want to remove it from the circulation. So requirement, all three methods, next IP, add IP, delete IP, should have time complexity fixed. So it should be really fast. And idea use two data structures, list and dictionary. So we have list and we have dictionary, my list and my dict. So my list lists of unique IP addresses, and dictionary with elements like this, IP address and its position in the list, where index is position of IP in the list. So my index equals 0, last position in the list. Okay, so this is approach. Okay, this is repeated. Okay, I guess I can just remove this. Okay. So this is idea. Okay, and this is the solution. So for example, should I go through it? When we do, so my IDX is a variable which keeps last position in the list. So when we go next IP, we always start with this, right? So what we do, we increase my IDX by 1. We're not supposed to get beyond the list length, right? So length of my list minus 1 will be largest possible IDX. If we go beyond that, so we return to the beginning of the list. So this is the idea of round buffer. We go in circles. And then we return the IP at this position in the list. Okay, so this is next IP. When we're adding IP, so if IP is already in dictionary, we don't have to do anything. We return an error, let's say. But otherwise, we add IP to the end of the list, right? And then we add it to the dictionary. So we say my dictionary of this IP equal position where this IP like was placed. Okay, and now the interesting thing about removing IP. So if IP is not in the dictionary, we don't do anything. Otherwise, we get position of this IP in the list. We get the length of the list, the last position. Then we popping another IP from the end of the list. We delete the IP which we need to delete from the dictionary, and then we put this IP from the end of the list in place of the one which we just deleted, and we update the dictionary with its new position. A little bit convoluted, but I love this program because it's using two dictionaries together. I mean, two data structures together. Okay, between two sets, and again, like pretty standard, we have two arrays A and B of integers. Task, find, actually not find, but just simply return the count of all numbers such that they're divisible by elements of A and elements of B are divisible by A. So you can think like B has very big numbers and A has very small numbers, and capital A is between them. So these numbers A are referred to as being between two arrays A and B. Your solution should return the number of elements A. And well, this is quite simple. We simply go from maximum A to minimum B, right? So we check all the numbers between them and we check if they're divisible or not, whether they go into this list or not, and we update the count and we return the counter. Okay, so this is really, really easy. I would say trivial, but this is kind of things you can get. And rearrange characters to keep them apart. Okay, this is interesting. So given a string and a number k, find if the string can be rearranged in such a way that the same characters are at least k distance apart from each other, right? So, well, the structure of the solution is you just call this function reorg string, and you give it string and you give it number k. So here I create the list, and actually there are each tuple is like a separate use case. So I say, for example, this is the string, and I need to rearrange. So for example, these characters MM, because they're the same, we have to put them apart from each other by at least 3 characters, right? And so on. So for each of these use cases, we do a reorg string, right? And let me mark it to make it visible. And this is the approach. And what we're doing here, well, we're doing the for loop, and we using max heap, as you can see, and we're using queue. So quite interesting. And again, I will not go through this solution right here, but this is what I wanted to show here, that one solution can actually use several data structures. Okay. Oh, okay. Maybe we can go through it. So what do? We create a char counter. Okay. For char in my string, if char we haven't seen it, we set it to 1. Else, if we already seen it, we increase. Okay, +1. Okay, so we create this dictionary char count. For each char, we have a count. Add all chars to max heap. For char and its count in items of this dictionary, we push to the heap, and the heap queue, I guess, heap push is from here, from heap queue module. Max heap. Okay, we started as a list. Remember, heap is actually stored in an array or in a list. Okay, and we put minus count for this character. Okay, and then we create queue, and then we start taking elements from popping from the top of the heap, right? And append them to the list, dequeue append. If length is k, then okay, I cannot follow it. And I need to concentrate to be able to follow it. Okay, embarrassing, but let's stop. It was a long day. Okay, so this is it for today. So these are the problems. I recommend to spend maybe an hour or two try to solve these problems yourself, trying to follow the solutions, because just being introduced to them is not enough. You actually have to do your homework. Okay, I will stop the recording.